So good morning, ladies and gentlemen, welcome back. We're going to talk about trigonometric identities. And first of all, let's take a look at this word identity. A lot of you will see things kind of weird because these are what's called proofs. They're called proofs. And in grade 10, the best connection is proving that triangles are congruent or triangles that are similar. And so what you had to do is you had to prove the left side must look like the right-hand side. That's the idea of these trigonometric identities. They're kind of like puzzles. And the word identity actually also means that it is true. So we don't give you things that are not true. In grade 11 and grade 12, we don't really give that to you, that are not true. The real world application of why we're learning this is like maybe in a court of law is proving that someone is innocent of a crime that they didn't commit. You might know that they're innocent and maybe you have the witness, but in a court of law, you actually have to show evidence and debate and describe and provide it, right? And that's what you have to do. Even though intrinsically you know that it's true, but in math, we try to show this. Another connection of where this trigonometric identity finds out is actually in philosophy, in the concept called symbolic logic. So when you use logic to prove things, this is what we're talking about. Although that, of course, is really, really neat and uses symbols and everything, we're not going to be talking about that. So let me just show you what one question might look like as an example before we get to it. I should have had one ready, but I'll tell you. Well, actually, let's prove this. So this is an example of a trig identity. In fact, it's actually one of the fundamental ones, but this is a trig identity. Now, one more time, let's do an inspection of what's given to you. There are actually no answers to this. This is actually what you see. And it looks like an equation, everyone agree? It looks like an equation, right? But that's not how you're supposed to treat it. The main goal for trigonometric identities is to prove the left side looks like the right side. Or vice versa. The right side looks like the left side. Okay? So unlike an equation where some of you realize you can manipulate left side and right side and left side, you can do things whatever you want, it's not an equation. And that's the hardest part for a lot of students. And this is the format that we'd like to try to show you. So we're actually going to prove this definition, even though you don't know any of the identities right now. And so what I'm going to do is choose a more complicated side. Now, the more complicated side in this case, it's really up to you. And when you do these trigonometric identities, ladies and gentlemen, you might actually get a little stumped. So just revisiting, coming back to it, and trying something else might be helpful. And so I'm going to give you some tips and strategies, and there's no one way to do it. For this one, just to tell you, the right-hand side is the more complicated side. So what I'm going to do is to prove this. The left side, I'm going to leave it as tan theta, and the right side is sine theta over cos theta. Now notice, I cannot change up the angles, right? Notice it's kind of like a puzzle. Don't get me wrong, in grade 12, they'll introduce other angles, a correlated angle, if you will. But right now, in grade 11, this is how it's going to look. Now this proof that I'm going to show you, it's a little weird because by definition, this is actually what we're going to get to. So this is actually something everyone's going to memorize. This is called the tangent identity. And you'll eventually just know it innately. But let's just talk about sine and what cosine is in terms of their basic understanding. Well, basic understanding for the right hand side, sine by definition is the opposite over hypotenuse. Right? That's sine theta. Divided by, what's cosine theta? Can I get a help from the class? Definition, just basic definition.
Adjacent over hypotenuse
Is correct. Now I could have used the x's and y's and r's and everything, but I'm afraid I'm worried that some of you are not used to them, which is fine. A lot of students, and maybe in the packet, have used the x's and y's and r's, but I don't like using that for this proof here. Now a lot of you see this example here on the right hand side, opposite hypotenuse. When you divide, you multiply by the reciprocal. And a lot of you realize what I'm trying to do, and I'm taking a lot more time than necessary. The hypotenuses divide out, and we're left with the opposite or adjacent. But then the left-hand side, we have to manipulate because technically it does not look exactly like it. So the tangent by definition is opposite or adjacent. That's the TOA part. And notice the left side does look like the right hand side. Since the left side looks like the right hand side, identity proven. And so this is an example of an identity. I'll be honest with you, most students do not go this deep into the basic foundations, but this is a good one just to explore. And notice what I didn't do. I did not move numbers, like I did not multiply both sides by cosine, I did not divide both sides by tan, I did not add and subtract, right? I manipulated one side and another side. Okay? Any questions before we move on? Any questions? So this is like your first real exposure to trig identities. So there's a couple other there's other identities that you need to worry about, and we're almost getting done for today. And I'll rewrite this again. I'll leave this on the chalkboard. First of all, there's the reciprocal identities. And they're as follows. Cosecant theta is equal to 1 over sine theta. Secant theta is equal to 1 over cos theta. Cotangent theta is equal to 1 over tan theta. The tangent identity. A lot of you know that we've just proven it. Tan theta is equal to sine theta over cos theta. Cotangent theta is equal to cos theta and so on. So these ones in blue that you see on the chalkboard, they're actually in your package, I think, and they're in your textbook where it says trig identities. And so a lot of students actually use this as their toolkit to solve the identities. There's one other famous one. It's called the Pythagorean identity. And it's actually related to the unit circle. A lot of you know Pythagoras is a squared plus b squared equals c squared. But just to speed it up, this one is sine squared theta plus cos squared theta equals 1. Now this is your first exposure seeing a power of sine squared theta, so let's introduce that really quickly. In math, this sine squared theta is the same thing as sine theta times sine theta. So some students wonder, why don't they write it like this? Which is correct. In the calculator, if people were to do this, unfortunately, the order of operations says that this squaring affects the theta. So to ignore that, we tend to write the squaring here. So it's just the way that we write it. But this is what this means. Okay? And that's why a lot of you kind of can see it a little bit. Well, r squared, of course, is the radius or the distance of the unit circle. And a lot of you kind of realize that the distance traveled, if we introduced it from last part of the unit circle, the x-coordinate is cosine theta, the y-coordinate is sine theta. But we'll talk more about that in detail. Here are the tips, and I'll just write them out on the chalkboard, and I think that'll end our day for this, but we'll practice this next day online. Tips. Work on one complicated side. Work in terms of sine and cosine. Remember algebra. Expand, factor, difference of squares, conjugates. 4. Is Pythagorean identity. Pythagorean. And last but not least, if stuck, manipulate other side. And so these hints that I'm trying to show you, they're not written in stone. And we really don't care how you prove it as long as the left side looks like the right hand side. To prove that the left side looks like the right hand side. And I think I wrote on the screen, so that's what we wrote in the tips. And you'll see it when we actually do more questions. So to give you an example of maybe what a question you might have to do to finish off for today, and I apologize for erasing this. Hopefully you guys got a chance to look at it. Because I've actually memorized it, but you would have them on in your notes and stuff. So this is not really an identity. It says just to simplify the following. So watch what I'm going to do. I'm going to give you cosecant x times sine x plus secant x times cosine x. Right? So this is not identity. This is just a simplification question. So what would I do? Well, it's not identity, but it's a second rule here that most students would actually use. Work in terms of sine and cosine. It tends to be the easiest one to do. So cosecant x is 1 over sine x. You agree? Times sine x plus, and then secant x is 1 over cos x times cos x. A lot of realize these actually divide out. And that's 1. That's 1. And 1 plus 1 is 2. So notice, technically, the identity could have been this question. Watch what I'm going to do. Erase that, apologize. This could be the identity question for this one. Prove. Some of you are slowly seeing what I'm doing. I just rearranged this question, but notice that an identity, it equals something. It looks like an equation, but it's not. You're supposed to make the left side look like the right hand side.
But that's not. Negative 1 equals 1.
Oh, negative. Look at the negative. Much better. Sorry. Everyone okay?